Hello everyone, the problem we're looking at today is the USACO 2019 February contest gold problem 2 of dishwashing. And actually there's two methods to solve this with different complexities. The official solution used a method that has linear complexity with 10 being 10 to the 5th power, with n being 10 to the 5th power, and my solution that I'm going to be explaining today has complexity of n times log squared. Even though it's way worse in terms of time complexity, but I think it's actually the more practical way, and if you actually see problems like this in an actual contest, I think the log square way is going to be easier, more straightforward, and easier to implement. So I will still be explaining the linear way, but that'll be tomorrow. So in this video, I'm going to be explaining the n log squared way of this problem today. So you can pause the video first and look at the problem. All right, so basically you have n plates and these plates are being washed. Bessie is washing the plates and then LC is rinsing the plates. So basically now you have three sections. You have a stack of plates that are not cleaned yet, and then you have a counter for the, no, that's too tall. Once again, you have a counter for plates that are not clean, a counter for plates in the middle, and a counter for plates that are clean, right? Because there's two steps, and there's an order that plates are placed on the counter. There's a label for every plate, and now you can only choose for every plate that you put from the uncleaned to the half cleaned stage. You can only choose to put it on top of an already existing stack or create a new stack on the right of the rightmost already existing stack. And every time you take a plate from the middle stage to the last stage, you take it from the top of the leftmost one, and then you put it onto the final stage. And now you're trying to make the plates go in order of their numbers, basically the order that they were in the original place as they are in the final place. And you can only move plates in those two ways, as we said, and you're trying to make the longest prefix in the input array be ordered. And now you're trying to find what this longest prefix possibly can be. So you can pause the video once again and maybe look at a sample so you can understand the problem more, and then get this problem and try yourself first. All right, as you thought about this problem and looked at samples, so basically the first thing that I noticed, even though I don't know why, I think it's just an intuition thing, but I feel like binary searching. Because I feel like if I don't binary search the answer, I don't know when I should start taking a plate. Because if I binary search an answer, say for this prefix 425, right, and then the order is just going to be 2, 4, 5, and then I know that once I meet 2, I can take it. But if I don't binary search what the answer is, I don't know if I should take it when I have 2. So that's my first idea. I think I should binary search the prefix. And now it leaves us with at most log n complexity for the checking, because we already took a log for the binary search, and now we have n log n for checking. And there is an algorithm that you can implement for checking the n log n complexity, and that's the one I used right here. And it's going to be, first you have to observe two properties. One, a plate is never to be placed on top of some smaller plate, because then this plate will always be taken before the smaller plate, and that conflicts. And secondly, a plate is never to be placed to the right of a bigger plate, because we always take the leftmost stack. So if this plate is placed to the right of a bigger plate, then this bigger plate is going to be taken before this current plate is. So if those two rules are satisfied, it's pretty obvious that we can basically get them ordered. So it's necessary sufficient. That's what we're going to call it. And knowing this, we can actually binary search where we put each plate, because it's just going to be the first spot with a plate number bigger than the current one. Because you can't put it on smaller ones, so obviously you can't put it on previous piles because this is the first spot bigger than the current one. And you can't put it on the right of bigger plate, so you can't put it on the next pile. So basically what I'm saying here is basically you have several piles right here, and each pile we only keep track of the top number, and they're like stacks, right? I used an STL stack, I'm pretty sure, to maintain them, and we're gonna put it on the first top that's greater than this current plate. Let's make it green, because if we put it right here, we know that this top is greater than it, so obviously this is on the left side of this current plate, and according to the second rule, that doesn't work. And we can't put it right here either, because we know this is the first one. This plate is the first one to be greater than our current plate, so this one must be smaller, and that conflicts with the first rule. So according to the two observations, or the two rules, if you call them, that we discovered earlier, we know that we can binary search the first stack with top plate with bigger index than the current one, and we place it on there. And binary searching, either you set or you just use an array, but actually binary search. But either way, you take another log complexity, and then you have to obviously go through all of the place in the first mid that you binary searched. So the complexity is going to be n squared, n log n squared. So even though this algorithm still passed with m being 10 to the fifth power, is not the optimal, as I will be explaining the linear complexity, which reduces 2 logs, which is quite impressive, tomorrow. So here's my implementation. I actually created stacks, and I used a set to maintain the place we have right now. No, to maintain the top of each stack. Yeah, and now it's easier for me to binary search where the top is, and then we just put it on there basically. And this code, along with explanations, will be posted down in the comments below. So if you think that will be helpful, you can go to comments and look at the code along with part of the solutions that I have written up here. All right. So basically, this problem is not that difficult considering that it's a Febuary and gold, but it's 2019, so that's reasonable. And all you have to notice is, first of all, you can binary search the answer, and after binary searching, if you just follow the 2 very simple observations that we made there, we can basically simulate this whole process. And as long as we go through all the places we binary searched, we return yes with the check function. Otherwise, we return no. And we return no when the 2 conditions obviously conflict. So after that, I hope you know how to solve this USACO 2019 Febuary contest gold problem 2 of dishwashing in n log n squared complexity. And the linear complexity is going to be explained tomorrow. Thank you for watching. Alright, I hate to say this, but unfortunately I did not grind today. And this has not happened, I don't think, all the way until December 19th. Ever since December 19th, I've solved at least one new problem every single day on USACO, either silver or gold. And today is January 8th. So it's been almost a month now that I've done problems every single day and done like a lot. Like 3-4 hours probably a day. And now today is gonna be the first day within probably 20 something that I'm not grinding. And this is sad, but I really don't have time today. I have now that school started, there's a lot of other stuff going on, and now every single day I'm just losing more and more confidence in the January contest. I really don't know what I'll do now if I'm just making progresses like this. And yeah, but I really don't have time today, and that's all right. Tomorrow I'll finally not have anything, I think, and I can grind probably. All right. Thank you for watching. Bye.